Sean Flack, one of the systems engineers at Arista, and I'm going to be talking about building routing, not trying to build routers. So quick look at merchant silicon. So Ethernet is a transmission data technology of choice, a de facto industry standard today. This homogeneity was leveraged by ASIC vendors to produce chips that could evolve by providing Ethernet-only connectivity. This removes all of the complexities brought in by other legacy or traditional technologies, each of them with their own encapsulation, transmission specific requirements, and the need for a customized hardware to be implemented. By focusing on only one transmission technology, hardware vendors have been able to deliver chips that are more sophisticated, performance, and scalable with every new generation. These chips are becoming fully capable, more economic replacement for custom-made ASICs. And these advances in merchant silicon technology has allowed Arista to introduce its devices to the market. As many of you already may know, we use merchant silicon within our products. We use the best chips available in the market in relation to the use case that we want to address. And since the availability of the ARAD chipset around 2014, Broadcom has proved its capability to deliver performant, economical, and flexible ASICs perfectly suited to address complex use cases, typically ones that are business as usual in service providers and in the WAN. Broadcom has such a huge market, and it makes sense for us to take silicon from vendors such as Broadcom and concentrate on our software engineering and get the capabilities and features out of these chipsets and out of these packet processors. At the end of the day, we're a software company. We obviously build switches and routing platforms, but yeah, we're trying to develop our features into the software. So let's talk about how the stack of technologies implemented in networking devices has evolved. First of all, we've already discussed about how we have moved from a variety of link data types or data link types to one and only Ethernet. When we come to the upper layer technology, we can say that IP is pretty ubiquitous in both LAN and WAN, whereas MPLS is very common in the service provider market, where it was used to virtualize the infrastructure amongst other different end users. In the control plane and the service plane, the situation is has been a little bit more diversified, mostly because of the kind of services that had to be made available to customers. Of course, an IGP protocol was needed to provide IP reachability, and BGP started to become more and more used not only for external peerings, but also to distribute internal routing information. But other protocols have been needed as well for both transport and service setups, such as LDP and RSVP, that have been used to distribute labels and to provide services such as layer 2 point-to-point and multi-point to multi-point, and traffic engineering using LDP and RSVP. So where RSVP can be defined as a transport protocol, we can state that LDP is both transport and service capable. Where traffic engineering was an absolute need, RSVP had been used despite its resource-consuming nature and other weaknesses, but at the end of the day, it's very ubiquitous and still works very, very well. And besides this, BGP started to play a big role in the service provider area. New address families have been added to provide new capabilities, and the most famous are related to L3 VPN, L2 VPN, and VPLS. So how does it look today, kind of moving from this, I guess, collection of protocols? So today, once the physical and the data link and once the physical data link and network layers have become homogeneous, the industry started to target more simplification at the control plane, or to better say, the overlay. These efforts have materialized in two technologies that we support alongside LDP and RSVP, that are segment routing and Ethernet VPN or EVPN. These have solved some major control plane problems. They've managed to simplify the networking stack, as segment routing doesn't need a dedicated control plane for label distribution, and the information basically needed to build SR paths are carried in well-known IGPs, which are extended accordingly. It's able to carry the actual state in the data plane and not in the control plane, and also segment routing can provide still fine-grained traffic engineering capabilities too. Long story short, segment routing can replace both LDP and RSVP without adding any new protocols to the stack. BGP has also become more widely used. It can, of course, provide the well-known IP routing capabilities, but it can also do a lot more today. It is the protocol chosen to implement EVPN or Ethernet VPN, which was originally born to provide a more efficient way to create multi-point to multi-point layer 2 transparent services amongst different data centers, but it has come a long way since then. And it can also provide all the capabilities needed to replace other technologies such as multi-point to multi-point, layer 3 VPN, and point-to-point services as well. By using a single address family, it's possible to get rid of other control plane machineries to provide the same set of services. So to summarize here, Arista now support both traditional service and control plane protocols such as LDP and RSVP. They're all supported, and more recent ones such as segment routing and Ethernet VPN over IP, IPVXLAN, and MPLS. And of course, all of this running over the one and only Ethernet. So let's look at how Arista has evolved from the data center into service providers and the WAN using these additional technologies. First of all, we have already discussed about how the modern internet requires the very same principles that are common in the data center, such as scale out, simplification, and software-driven features. And these are places where Arista belongs by its nature. But today, thanks to the advantages in merchant silicon that I've already mentioned, Arista can also offer tremendous performance, flexibility, and scaling on top of our R series platforms. So these are the 7500R, 7800R, 7280R, and also now the 7020R, which is a 1 and 10 gig optimized platform, which can offer the same feature set as its bigger brothers, but at a fraction of the cost and in a much smaller 1 gig box with 1 gig and 1 gig and 10 gig ports on there. And last but not least, all of these platforms, from the multi 400 gig platform to the smaller 7020R that I've just mentioned, run a single operating system EOS. We've been developing this open, extensible, and flexible control plane around open standards, real-time visibility using streaming telemetry, high quality development, and also sporting a full set of industry leading automation technologies out of the box, such as netconf, Yang, GNMI, OpenConfig, Python, Ansible, and many more. So to give you a very quick example of kind of looking at a different way of architecting a WAN or a service provider network, and there's definitely not enough time here to explain it in too much detail. But here's how we can leverage some of the more recent EOS innovations to build a new USB or a WAN network architecture. These parts are basically built upon a distributed leaf spine POP architecture, whereby each POP is represented as a single node by virtue of dynamic flooding and IS area abstraction. I'd say check these out or ask some questions after the session. This gives an elastic and scalable architecture that fits any size network, but most importantly, its true reliability and scale is built into the architecture and not in the design or using software kludges. What's great is that this architecture seamlessly correlates with the recent MPLS enhancements, which are also part of EOS, such as segment routing, Anycast SID, ISIS loop-free alternative, BGP segment routing, traffic engineering, and many more. So lots of different features there to build this kind of scale-out architecture. But more information about this, please ask in the questions. So finally, everything we spoke about today is supported on our products. We are building routing into our platforms and are not trying to build routers. To achieve this, we believe we started from a solid foundation. First of all, the most important pillar was the modern OS. EOS, all the components of the OS running user space. There is no kernel involvement at all. All the modules have their own dedicated CPU, time, and memory. It's also fully programmable at the control service and data plane using open APIs and well-known languages. And today, just to finish up, today Arista can offer carrier class scaling to its customers. We have released full 64-bit EOS implementations to overcome the 4 GB RAM memory access limits, and which has enabled us to scale up to 30 million prefixes in the RIB. And then thanks to the merchant silicon that we've been using, we can fit 2 million prefixes in the fib with up to 512 weight ECMP, if you need a network that large. And also this has been implemented through the use of Flack, which basically augments the hardware and software to get to these types of scaling numbers. So last but not least, we know very well certification it can be difficult. Therefore, Arista offers virtualized and containerized versions of EOS to allow network engineers to build even very complex networks virtually. It's perfectly possible to use open source virtual lab solutions such as GNS or EVE-NG, or also to spin up virtual instances in GCP, Azure, and AWS. So it just leaves me to say, please go ahead and download the virtual images that you would find via our website. And I will hand back over to Keith. Thank you very much.
Okay, thank you, Sean. We have time maybe for just one question. We have one question from one of the other speakers. Fergus, do you want to go? Sean, are you okay to take that?
Yeah, sure, go ahead.
Fergus, do you want to read that question out, please?
Okay, the question's from Tom Strickland, I think. Will Arista continue being a sort of systems integrator for hyperscalers and sell those products? Example being a mini-pack Arista 7368 product.
So if I'm understanding the question correctly, so the question more about whether we're going to be packaging the devices with servers, or is this more about? So could you repeat the question again? Sorry.
Will Arista continue being a sort of systems integrator for hyperscalers and sell those products? Example being the mini-pack Arista 7368 product.
Very much so. So the 7368 is it's a current product and something that we are also developing into the next generation of that product that uses the Tomahawk 3 chipset today. That's going to evolve into the Trident 4. So to answer it, I guess the short answer is yes, we're going to be continuing that product and still packaging that product, but it's definitely relevant to other people as well, the 7368.
If I can follow up on that, the main thing is that it's my understanding that Arista developed the 7368 in conjunction with Facebook specifically for their F16 architecture. Is that something that Arista will investigate further, as in have those relationships with hyperscalers where you develop specific platforms with specific ASICs to then sell that to a wider audience? Because you do seem to think that platform is quite relevant to others as well, not just Facebook or other hyperscalers.
Yes, I think again, it's something that we would like to do. And it's really the ability to run, say, the FBOSS operating system on that switch, or you can run the regular EOS image as well. So I think there'll be some more news around different OSs that can run natively on our switches as well. And I think there have been some announcements already around that. But it's definitely something that we would like to continue doing. But at the same time, we want to be relevant to everybody, right? Whether that's in the data center or whether that's routing platforms that I've been talking about today.
Okay, and we have another quick question from Brandon Butterworth. Would you pitch these against the Cisco 8200 or an MX as core?
100% yes. Yep. Yes. So that has become definitely something that's happening more often as well, where we're pitching these against the likes of MXs, NCSs, ASRs for core, I'd say traditional routing, core traditional kind of services using RSVP fast reroute traffic engineering, and also using them kind of in greenfield setups where we're looking at segment routing and EVPN. But the point, I was making today is that we support some of these newer technologies, but are also supporting the more traditional services as well, like RSVP and LDP.